And the purpose of this assignment is to model a machine learning algorithm to be able to predict prices for housing. And the data we're using here is the California housing data from California Census. So let's move on to our data and see what we have here. We have 9 different parameters, and 8 of them are numerical values, float type. One of them is an object, which is the ocean of proximity. And then for each of these, we have this number of rows, but for total bedrooms, we have less rows, which means that some of the data here are missing. We'll get to this later. For now, let's move on to the next part. But before that, here we drew histograms for different data parameters of our data set, and we'll get to this later. The next section here is to create a test set, which consists 20% of our data that we're setting aside, and we're using it later after our modeling is done to test our modeling and see how accurate it is. And then we keep working on our training data. But first of all, we need to make sure that our training data set is a good representative of our whole data set. So here we draw the same histograms for them, and we can then compare it with the original histograms that I have here on the right side. And in the first glance, we can see that they're all perfectly similar. So we can say with confidence that this is a good example and a good representative of our overall data. Okay, now moving on to this part, which is the stratified random sampling method. So from our data, actually from the next part here, we see that the housing pricing is highly correlated with median income. And to look at it in more detail here. So yes, and here we can see the correlation number, which is almost 0.69, and it's relatively higher than other parameters. So here we categorize our data into different groups in terms of their income, so that we make sure that this highly correlated parameter is perfectly distributed in the training set, similar to the testing set and the overall data. And from this diagram from before and this one from after, we see that it's the same distribution. So we've done good here. Moving on to the next part, here we're doing an explanatory data analysis to see the relationships between our data and be able to run a better machine learning algorithm. And from here, we're just looking at the correlations. However, the correlation doesn't work for the categorical ocean proximity parameter, so I had to drop that to be able to take a look at the other correlations. And the highest correlation here, as I mentioned earlier, was the median housing value to median income. And this line that you see on the top is actually because the values above 500,000 were capped to this point. So that's why there's a line here. Moving on to the next part, here we have to prepare our data for training. And this includes a few different steps, and they're called data cleaning. So the first one, as I mentioned earlier, we had some missing values. And here we have a few options to deal with that. One option is to get rid of the attribute altogether, which doesn't seem like a reasonable solution. And another approach is to get rid of the rows with missing data. But doing that, we're also missing the rest of the data in those rows. So we don't want that. So the best option here is to replace those empty cells with data of the average for that parameter. And in this way, our model wouldn't be impacted. Moving on to the next part, this one is handling the categorical test parameter of ocean proximity. And here we start with using an ordinal encoder, which basically assigns numbers to these data values, the text. But the problem with this one is that it assigns number in the order of alphabetic for these words, and numbers carry a meaning with them. So when we assign the least number to the first word in the alphabetic order, we are kind of giving the perception to the model that it's a lower value, but it's actually not, because we don't care what that data starts with, what that name starts with. So in order to prevent this problem, we use another function here, which is called one-hot encoder. And this one assigns numbers in form of an array of zeros and ones to each of the 5 different values of that parameter. And it fixes our problem. The next one is customer transformers. So this is for the case where we engineer new parameters that are more correlated with our data than any single parameter. For example, in this case, we saw that our output data are not highly dependent on the number of rooms or the number of bedrooms, but then we customize this other parameter, which is total number of bedrooms per number of rooms. And that one gave us a relatively higher correlation with the output parameter. Moving on, the next step is to do a feature scaling. And this one basically means that our data have different ranges and different values. For example, our housing pricing values are significantly higher than the rest of the parameters, or our income values are relatively high. But on the other side, our number of rooms or our number of households are relatively lower. And it would give the right perception to the model that those larger numbers are more important, and the model would assign a higher weight to them, but we don't want that. So in this feature scaling part, we basically change the range of data for all the parameters to pretty much a similar number based on their average and their standard deviation to prevent that issue. And then eventually we put all of these into a pipeline, basically workflow to do every time we run the model and prepare our data for and clean it for modeling. And last but not least is the modeling itself. So we picked a few different machine learning algorithms here, starting with a linear regression. We see that the prediction and the actual data are relatively different. So in order to see how accurate our model is and how much our error is, we calculated the root mean square error, and it gave us this number, which is actually relatively or very high. So we decided to try a decision tree, and this one gave us a 0 root mean square error, which basically shows that it's overfitted, in contrast with the previous one, which was underfitted. And neither of these are perfect matches for our modeling here. And the reason that decision tree gives this very low root mean square error here is that decision tree algorithms can get to the point that there's one branch for each row of data. And that's not what we want. And we probably have to limit our decision tree at some point to give us a better solution. So I tried an extra algorithm here, which is a random forest. A random forest algorithm is basically a set of different decision tree algorithms, and that's why it's called a forest. But getting into the root mean square error for this one, it's actually lower than the one for the linear regression, and it's not 0. So it's better than those two, but I guess it's still not perfect because it's relatively high. And I believe that we will learn what algorithm is perfect choice for our modeling in the next sections of the course. Thank you for listening to this.